So, good morning. We continue from where we left last time. Last time what we did was we reworked on the concept of derivative and then looked at some simple things. And most of the time we spent on understanding what this derivative is all about. And before we go further, maybe we would give a pictorial view of what the derivative is. Okay. So you recall, let us take f from R. Now we can draw the graph of this function. We assume f is continuous or smooth or whatever you want. So this is R cross R, and we can draw the graph of this function, something like this. Okay, so let's take a point x here on the domain. So this point is actually x, f of x, or the value of this point is f of, it's actually f of x, 0 f of x. This point is x0 and this is the point. Now what is f derivative of x? F derivative of x is the limit that we have, and it is the slope of the tangent f at the point x fx. The graph of therefore what you have is, you have a line here whose slope is given by f derivative of x. Now you can write down the equation of this line. This equation of this line is y minus h, okay, where h is of course the neighboring point x plus h you take, and then this is the increment that you make and so on, and you have this kind of relation, that's f dash x, y is equal to okay, so what does this mean? So if you look at, let me magnify the picture, something like this. So I have the slope, this is the line with the slope f dash x, and what I have is this. See, if I take x and x plus h, then this distance is h. Let me be a bit more, rework the picture, bit more, make it more transparent. So I'll just make it look like this. Okay, give a deeper line. So what happens? Okay, let me do this. Now this is your x. This is say x plus h, and then you take this one. So this distance is h, and this height that you have, okay, this is fx plus h minus f of x. This is actually what you are used to writing delta y. So it is written in terms of this. So you take f of x plus h, and this is your f of x, and therefore this is the distance that you have. Okay. So you have a line whose equation you can write, and that line, the tangent line, approximates or in short, locally you are approximating the curve by a tangent line. It's a linear approximation that you are seeking, and the linear approximation is defined by the slope of the line and the point where you have the tangent, and so you can write down that and you can easily check this. So this is the sort of geometry that you come across. In a more general scenario, you are not in a position to draw the picture. Even for R2 to R may be possible, but when you take it from say higher dimension spaces, a picture is not, a pictorial representation may not be possible. Okay, so let us work on the idea of the partial derivatives now. This is where I left last time. So what was the partial derivative defined? Partial derivative was defined as the directional derivative along the coordinates. So if you have, so you had these things like df by dx in R2. You are familiar with this. Or more generally, if you have, say, in Rn, if you have a function of x1, x2, etc., xn, then you can define df by dxj at a particular point, or if you want, you can call this df djf. This is the notation that we adopt. Okay, so you can talk about, so where f is a function from Rn to R. Or more generally, if you are working on a function from Rn to Rm, then you can talk about the partial derivatives of each of the component real valued functions, and that I will introduce the notations too. So one of the things that you can immediately see is that if a function is differentiable, now we are taking f, some open set E contained in Rn to Rn. Our usual notation. So x belonging to E we are working on. Then you see differentiable in the sense in which we have introduced the definition. You can talk about the directional derivative. What is the directional derivative? Suppose, let us take a picture. Assume this is Rn, so I am not able to draw the picture of Rn. But what I have is, I have a unit vector taken in some direction, say you call this, and fix this vector. Now, along this line, the points are Q for some t belonging to R. So, as t tends to 0, you see that this point approaches 0. Now, you can talk about the derivative of the function f along this. What will be that? See, it is going to be f of okay. So, you want to consider the function at a point x, then you can take the line passing through x with a slope which is parallel to this line, so whose slope is determined by the vector u, okay, and then you can compute the derivative there. So what happens? So you have got f of x plus pu minus f of x so you can, now what you can do is, okay, so what you have some a, what is the increment that you use? It is tu, a acting over tu, so it is actually a times, since a is linear transformation, this is t of au plus error term. H is what? H is tu. Okay. So limit of this goes to 0. As tu goes to 0, which in turn means, because u is a vector with is a unit vector, so u does not go to 0, but what you have is that limit to 0. That's exactly what we do. But this part I can replace by t times au, because a is linear. Okay. So what do I have? This is what it turns out to be. What I am saying is that r of tu, norm of that divided by norm of tu goes to 0. And norm of tu is this, that is r of goes to 0, t goes to 0. This is what you have. So, if such a linear transformation exists, then this is what you call the derivative along the direction along the direction. So then if this limit exists, then this is what you call, a is called So you see that if f is differentiable, then this type of relation holds. That is f of x plus h minus f of x minus ah, the norm of that goes to 0. Okay. So this is what you have. So minus ah goes to 0, or this is equal to, you have a this term, so this is equal to, so you, what you have is f of x plus this is the what you have, what you call the derivative, existence of the derivative of this. So if this happens, in particular it will happen for tu, and let t tend to 0. Okay, so all directional derivatives exist. So f differentiable x. In particular, all derivatives along the coordinate directions exist. By which I mean, you have got in Rn, suppose E1, E2, etc., En is the standard basis. Then you are taking the direction, you are taking as, say, E1, E2, etc., En, and computing the derivative, and they are what you call the partial derivatives. These are the partial derivatives. Because you see, in our development, we define derivative in the conventional way, just along the one dimensions, and we extended this for functions of several variables by taking what is called the partial derivatives or derivatives along the coordinate direction, and that was directly possible. We were in a position to define it easily. So now we have translated everything into the differentiable functions, and for differentiable functions all partial derivatives exist. Okay, so that is something that is assured. So the one of the questions that you ask is, if the partial derivatives exist, then does it imply the function is differentiable? That is the question that you ask. So we have seen this example. Zero. This is equal to xy divided by this example we considered last time, and we have seen that this particular function we have observed that f is continuous along the x and y axis at 0, 0. That we have seen. This is very easy to see, because the value of the function, if you take the coordinate axis, say if you are taking a point like this, okay, if you are looking at the point 0, 0, and the coordinate along the coordinate axis, x axis y equal to 0, y axis x equal to 0, therefore the function is defined for all values along the coordinate axis as the zero valued function. Therefore, its derivative along these directions are going to be 0. So, they do exist. But we have seen for this function, suppose you take say the line x equal to y, okay, then you can easily check that the function takes the value along x equal to y. This is xy, this is x square plus x square, so it is 2x square. So, you have x square divided by 2x square. So, the value of the function is along this line, it is given by half. But the value of the function at 0, 0 is 0, that is given to be 0. Therefore, you see that the function is not continuous along any radial line other than the coordinate axis. Okay. So, simply the partial derivatives exist does not imply that the function is differentiable. Whereas, if a function is differentiable at a point, then all the partial derivatives exist. That inference you can make. Okay. In fact, all derivatives along all radial directions would exist because the function is differentiable. And I was telling last time, it's an awful restriction that you are imposing, and for the existence of partial derivatives, our demand is much less. Okay. So, we have seen an example where the existence of the partial derivatives does not assure the existence of derivatives along other radial directions. Therefore, in particular, the function is not differentiable at 0, 0. Now, this is okay. No, I didn't mean that. So, what I said is the function is not continuous at 0, 0. Right. The function is not continuous at 0, 0. That's what I said. Okay. So, you cannot really ask for bigger things actually. Right. So, what you have, the function is not continuous at 0, 0, which means the function has continuity along the coordinate axis, but it's not along the radial directions. This is what we have observed. Now, later I will make a remark. We are going to get an inequality which tells that if a function is differentiable, then it is necessarily continuous at that point. So, all differentiable functions are continuous functions. So, we will I am not giving the proof of it at the moment, but soon I will give an inequality which will prove this. So, just don't think that I am just, but I am going to use that result. Just with a caution, I am just using that result, but soon I will rectify the absence of a theorem to support it. It is not a surprising theorem anyway. But so, all differentiable functions are continuous. So, continuity is a consequence of differentiability, whereas differentiability, therefore, it is a necessary condition for differentiability. So, if the function itself is not continuous at 0, 0, it cannot be differentiable. Okay. So, the differentiability is not guaranteed. Whereas, you can easily compute the derivative along the coordinate directions, and you see that it's the partial derivatives are 0 for the function. Okay. The example the partial derivatives exist. Along the coordinate axis. Exist because what are the partial derivatives? It's simple. The function is identically 0 along the x-axis, the function is identically 0 along the y-axis. So, certainly at any point the derivative, the partial derivatives are going to be 0. So, there is no difficulty, they do exist. But that does not mean the function is differentiable at 0, 0. You see that it is not even continuous. Not even continuous when you work along other radial directions. This is what we have seen. So, the function is not differentiable, but I will support the supporting inequality soon, because we have to do something like mean value theorem. So, what we have is, in fact, this is what you have. So, this is the theorem. So natural question, what is the next question? The next question is, if the function is differentiable, then all the partial derivatives exist at that point. But we have seen that the mere existence of partial derivatives is not going to assure you that the function is differentiable or even continuous. Therefore, forget about differentiability. Okay. So, you ask this question, is it possible to impose further restrictions on the partial derivatives to assure differentiability. This is the question that you are going to ask. Okay, mere existence of partial derivatives is not going to assure you that the function is differentiable at a point. So, can you put in something more to the existence of partial derivatives, so that you can, from that you can conclude the derivative exists. Now, this is done in the following theorem. I am not going to give the proof. So, let me just state the theorem. Let be open and f is differentiable okay. F is a map from E to Rm then we say that, okay, so let me write. If f is differentiable at a point x belonging to E, then the partial derivative is given by the following. The formula for that. Then di dj fi and this is what you have, f derivative of x acting over ej equal to sigma dj fi acting over u1. So I equal to 1 to 10. So let me just describe what I mean by this. Okay, f is a map from E to R. We are taking E1, E2, etc., En as a standard basis for E. E is contained in Rn. U1, U2, etc., Um as a standard basis for Rn. This is a standard basis for R. Okay. Now let me write this. Now you see that f(x) is f is a map from E to Rn. So this is equal to, it's a vector function. These are scalar valued functions f1, f2, etc., fm, and they are the components of that. And this is equal to sigma I equal to 1 to m fi x ui. This is the usual expanding f in terms of the standard basis. This is the meaning of saying that these are the components of this. Okay, right, for x belonging to me. Now what you have, therefore fix you can calculate. What you do is you take the dot product with f. So fix is essentially dot ui for now we write down what we have is this dj fi, this is equal to limit t tending to 0 of fi ej, taking the derivative in the direction ej, minus fi x, because ej is actually t into norm of ej is equal to 1. So if the limit exists, then this is what you call the partial derivative. Now this is the partial derivative of fi along the direction ej. Okay. So this is true for j running from 1 to n and I running from 1 to n. Okay. So what we say is that if the function is differentiable, this is what the theorem says, if the function is differentiable, then the action of f derivative of x, this is a linear transformation, how it acts on Ej is given by in terms of the partial derivatives. That is the theorem that you have. And therefore, one can write down the matrix form of this with respect to the standard basis in terms of the partial derivatives. Therefore, you see that if the function is differentiable, then it is intimately connected, or it could be given in terms of the partial derivatives. But if it can be differentiable, otherwise no. Okay. So that's the important part. So let me write down the derivative, then the matrix representation of f derivative, write it this way. I am writing this with respect to the two bases, standard bases. This is given by the m rows m by n matrix d1 f1 all these partial derivative exist, and using that you can write down the matrix representation for f derivative of x along the with respect to these standard bases. Okay. Now what one can prove is the following. So our question still is unresolved. Suppose you know that all these partial derivatives do exist. Can you say that it represents f derivative? It gives gives an impression that probably these two would, because the matrix representation you can write down a matrix using all these partial derivatives. Okay, but does it mean that f derivative exists? This is the question. And in fact, our example has already revealed to you that this is not a simple question that you can answer, because in general it doesn't exist. The existence of the partial derivatives do not assure you the existence of the derivative. That we have seen from an example. Then naturally there is a question. Then what else? What? Okay, so you can show that. So this is the theorem that you have which answers this question. Suppose you need some condition. Rm is open subset of Rm. Then f belongs to C1 E if and only, this is a nice theorem, if and only if dj fi exists and are continuous for less than or equal to m, 1 less than or equal to j, less than or equal to n. This is the theorem. See, f is a C1 function. C1 function means what? The first derivative exists, that is f derivative exists. Okay, and is continuous. That's what we are assuming. If and only if djfy exists and are continuous only. So the continuity, existence and continuity of djfis assures you that the function has a derivative which is continuous. The derivative exists and is continuous. Now this is a nice theorem which you can use. Now in the absence of, now you can check the or compare this against the example that we have looked at, that is fxy is equal to 0, 0, 0, fxy equal to 0 at, or f0, 0 equal to 0. This is the example. Fxy equal to xy in this case. You see that the function is differentiable function, the partial derivatives exist at 0, 0, and they are all identically 0 and everything is fine, but certainly still the function is not okay. So you see that there is a problem regarding the existence of the derivative, because along the radial directions it doesn't exist. That's the problem. Okay, right? So the function is not differentiable at 0, 0. Okay, so we will look at this. So that tells us the relation between the differentiability of the function and the existence of the partial derivatives of all the components. So now let us look at the let me just give you the inequality that talking about, which helps us to talk about the which enables us to okay, we said partial derivative exists does not imply the function is even continuous, and if it is not continuous, certainly the derivative does not exist. So let us write down the theorem. The theorem says that suppose f maps a convex set E contained in f is differentiable in E, and there is a real number M such that norm of f derivative x is bounded by M is less than or equal to now you see you have this is the generalization of the mean value theorem, okay, right? You can easily see that this is a generalization of the mean value theorem, but this is the only possibility that exists. So here you have got the norm in Rm, norm in Rm. So this is the estimate that you get. So what does it say? It says if E is a convex set. This is to assure that you take 2 points in this, then always the entire line segment lies in the set. That is why the convexity is used. And you see that locally if you are working on this, then what happens is that if you take a point, you can take a neighborhood. If it is an interior point of E and E is open, then you can take a neighborhood of that which is convex. Okay, so you can get a ball because you are working in R. Okay, right. So you have this convexity is one of the requirements that you have to ensure that for if you take points A and B, then the entire line segment lies on this. In one dimension, you have, what does it say? FB minus FA is equal to F derivative at some intermediate point times B minus A. That's the mean value theorem that you have. But here you cannot make that statement. Okay, that's why what you say is that you have set the whole thing in terms of the bound for f derivative in that neighborhood. Okay. So what do you mean by f derivative? F derivative you have, it's a linear transformation. For linear transformations you can talk about the norms because it's a linear transformation from Rn to Rm. So you have the concept of what is called the norm of this linear transformation, and that is what you write here is bounded by M. If that is so, then this is what you get. Okay. So immediately you see that if this is true, that is the derivative exists and is bounded, then you have continuity assured. F is continuous. As B A tends to B or B tends to A, you see that FB tends to F. Okay. So that's the consequence of this particular theorem. Now let me go to the next section, namely the I think I have spent some. Okay. Spent a considerable amount of time on this. Now let me just go to the inverse function theorem. Right. What does the inverse function theorem say? Certainly I have no time to attempt a proof of this theorem, but let me see whether I can give you some idea of how you attack this or how you prove this theorem or what the result is all about and so on. Let me give you a feel for this. Okay, let us go to the one dimension case. So you take f from R to R. You can take it as an interval maybe. So what you have is you draw the graph of this. Something like this. Okay. Now what do you, suppose you take this point, draw the picture, something like this. Okay. Suppose you have the line approximation of this f by the tangent, okay, which is determined by this point as well as the derivative of the. So if this point is x, then you are right, you have f dash x is the slope of the tangent to the curve at the point. Now what it says is the following, okay. You see that is this function invertible? Whatever I have drawn, is it invertible or is it one-to-one and on-to? It is not one-to-one and on-to. Okay. First of all, you see that it is not one-to-one, so that you can talk about the inverse. What happens is, you see that this point as well as this point maps to the same value, so it is not one-to-one. Okay. But is it locally one-to-one? This is the question that you are asking, so that you can invert it. Okay. If so, can you connect it to some property of the derivative? You easily observe that. For that, you observe the following. Suppose you have a function which is linear, something like this. Now you see that as long as, suppose the slope of this is m, okay, as long as m is not equal to 0, so you see what is the equation of the line? The equation of the line is y minus y naught x naught. So you have y written as a function of x, right? Here you can write invert it, provided m is not equal to 0. I can write this as x minus x naught equal to 1 upon m y minus y naught, provided m is not equal to 0. So if this line has slope which is not equal to 0, then you can invert it and write x as a function of y. Okay, so this is possible. Here you have seen that in a general function, even if the derivative exists at all points, is a differentiable function, you cannot, there are functions for which the inversion is not possible, because the function is not a one-to-one, is not necessarily a one-to-one function. So the next question that you ask is this: suppose the derivative, suppose the derivative of the function at a point is not equal to 0. Okay? There are several points where the derivative is not equal to 0, but that does not mean that the function is invertible. For instance, if you take a strictly monotone function, monotonically increasing function or monotonically decreasing function, then you see that you can invert it because you get a one-to-one map. Okay? Right? Therefore, what goes wrong is the breakdown of the, or what could cause a problem is the breakdown of this monotonicity by having some maxima and minima, extremal points where the derivative vanishes. So avoid those points. In that case, if you were to restrict, because this is the, see, suppose I draw the graph like this. So there are, between these 2 points, you see the function is monotonous, monotonically increasing, and there possibly you can make a statement, okay, because m is not equal to 0, but m is 0 at this point, m is 0 at this point, and there of course you are going to expect trouble. So what you can say is that if x is some point where f derivative of x is not equal to 0, then in some neighborhood of that point, however small it may be, you are able to invert the function and write y equal to fx can be inverted to write x is equal to some g of f. What happens? Okay, let us take this part. Then you see that you have image here. So this is the range of f when you restrict to the interval x1 to x2. Okay, this is fx1 x or y1 y2. So here you have an open set U, here you have an open set V. So you can claim that there exists an open set U here, there exists an open set V in the range such that F is a map from the open set U onto the open set V. Okay, so what you are asserting is that if at x, at some point x, f derivative of x is not equal to 0, then you have, you know, a point, a open set U containing x and an open set V in the range space, so that the map is from, the map from U to V is 1 to 1, therefore it is invertible. Now this is the inverse function theorem, and then you can talk more about the smoothness of that. Okay, so I think it may be clear in a different way. Let me put it this way. Okay, so let me state the theorem and then interpret it. This is the inverse function. We assume the following. F is from E to Rn. E is to Rn, sorry, but in Rn. So we are talking about functions from Rn to Rn, as we have done here from R to R. Okay. Let f derivative of A be here we have said f derivative at a point is not equal to 0, which since you see it's a one-dimensional operator, it's a scalar, and you see the operator is invertible if and only if that number is not equal to 0. So we have to replace that by this is an operator. So this operator is an invertible operator. You know that because you see that f derivative of A belongs to R into R. So we are talking about the invertibility. Let B be equal to f of A, where Then the assertion that we make is this, the first assertion. The first assertion that we make is this. There exists open sets U and V Rn such that A is an element of U and Fa, which is equal to B, is an element of V. This is the first assertion. And F is 1-to-1 on U and in short, what you are saying is that there are subsets U and V as neighborhoods of A and Fa such that the map F is a 1-to-1 onto map between U and V. Okay, what does it mean? The inverse exists. Okay, therefore the inverse exists. F is invertible and the second statement that we make is about the inverse. If G is the inverse of F, defined on V, by G of equal to X, then G is a C1 function on so let me just draw some pictures because that will give some insight into the problem. Okay, general pictures. Okay, that's what I mean. See, you have this, you take as Rn. Now I make another copy of Rn because I am also talking about the same Rn. Remember, it is not Rn. So I have a point A and see there is some subset E. E is an open subset of Rn. A is a point there. Now what you have is this. See, there is a map F defined. It's a C1 map. Yeah. What I have is this. Suppose I call this B, which is equal to F of A. Then what you can assert is the following. Okay, we assume, this is assumption, F derivative of A, which is an operator from Rn to Rn, is invertible. This is the assumption, this is the central assumption that you make. And once it is assumed, what you say is that there is an open set U containing A and an open set V containing B such that F is 1-to-1 and onto from u to so that the inverse map exists. Therefore, this is invertible and the inverse map is denoted by G. And then you have talked about the continuity of, that is, G is a C1 map and G is defined like this. G is a C1 map and you can have an estimate of, easily from this relation you can write down what is going to be the derivative of G at fx. Okay, so that I will write soon. But let me just tell you about the proof of this theorem. Now, proof of this theorem involves quite a lot of work, because what you are saying is that, what you are asserting is that in the neighborhood of u, this happens. How far you can go with u? Certainly, what you are going to prove is that inside u, the function f continues to be invertible. Okay? So, what we are going to prove is that in u, this is one of the outcomes of this, what you have. So, how do you prove this? Or you want to prove that this is actually a one-to-one map. There is the existence of a u, there is the existence of a v, such that this map is one-to-one and one-to-one. Okay. So, what do you have? How do you work on this? I will just outline the proof. I am not going to the details of the proof. There are a lot of things to be worked out. And you can go to my channel where I have spent several lectures to explore this particular, the proof of this theorem, and that will give you a lot of insight into working on this kind of scenarios. But I don't have time here to do that. So I recommend, or I suggest to you to go to my channel and have a look at the proof of the inverse function theorem. If I remember correctly, it may be about 3 or 4 lectures which I have spent working on this, and also I have, in the end, I have analyzed an example in all details. In fact, every step in this proof has taken a lecture which goes on for more than 1 hour. Okay, so it's in all details I have worked out this. But what I am going to do is just give the basic steps of the proof. So you are assuming this, denoting f derivative of a by a linear transformation, and a is invertible. So we choose a particular lambda such that lambda is equal to 1 upon twice A inverse is a bounded linear transformation, because A inverse exists and that's a bounded linear transformation on Rn, and its norm is what you are written here. So you choose, this is perfectly a choice that you make for making some conditions. I mean, you see, you are not saying that this is the best possible u that you can choose or any such thing. You are saying there exists a u, some u, and a corresponding u. Okay, right. Now you determine or define u by norm of where a set of all x for which minus a is less than lambda. So u you define as a set of all x such that this condition is satisfied. That is possible. Okay, so that is how you choose your u. Now the art of the proof involves the use of a beautiful theorem which is used in many such circumstances, namely the fixed point theorem. So let me prove the fixed point. I am not going to prove the theorem, I am just giving the gist of the theorem. So what this says is the following, and you see, you should also look carefully at how you exploit this fixed point theorem in the analysis, because there are many circumstances where fixed point theorems are useful, and if you are a researcher and you may come across situations where you can use these ideas. Okay, so what does it say? So this is a contraction mapping, simple. If X is a complete metric space and P is a map from X to X which is a contraction, it's a contraction means it has the property that 2 points are thrown to closer points. Okay, that is rho of rho is the distance function that you have in the metric space for x, y, and alpha is then there exists a unique z belonging to x such that dz, that is z is called the fixed point of the map T. Okay, so it's something like this. Suppose this is your x, you have a map T which has the property that it maps, say when you have x and y, when this is Tx and Ty, so T maps this to this point, T maps this to this point, and the distance between x and y is bigger than the distance between Tx and Ty. That's what you mean by contraction. And then you see that this map on the whole working on x has the property that there is exactly one point which has not changed its position. It's one of the powerful, beautiful theorems that you have. This is called the Brouwer's fixed point theorem. And on its own, it's a very interesting result. But we are going to use it, so I am not going to say more about it. Okay, so we use this. So we use this to prove the existence of, see what you do is you take some y here, you want to prove that there exists an x here. Okay. So how do you do that? It is done as follows. It is done through the use of fixed point theory. Okay. Now let me draw another figure. So we are now, I don't want to separate this now, right now. Draw another figure in the same space and then give an idea of this. So you devise a contraction mapping. This is the art. So this is essentially the construction that you have to do in this regard. How does this construction go? That needs a lot of to get an insight into what is going on. I would suggest you to look at the lecture I gave on my channel, where I spent a considerable amount of time explaining out these ideas, right? Okay. So you take, see, you have, this is Rn and E is this, okay. Now you define a map phi from as follows. What is it? The map is this. Phi of x is defined as x plus A inverse. A is invertible. Therefore, A inverse x is y minus x. Or you can write it this way. Now you immediately observe that, and you first of all observe that phi is a map from E into Rn, or from Rn to R. Okay. So if you take x, what you have is that y is equal to fx if and only if phi x equal to x. So y is equal to f of x if and only if that is x is a fixed point of so you are searching for the fixed points of y. Okay. So what you prove is this. You have A and then you have u as the neighborhood of that. As you have defined u, you can fix. Then you take v as, this is f of, you are inside R. Okay. What you do is you are taking up a point for a y in V, you want to show that there exists an x. Okay? So you want to show that there exists an x. So existence of x is to be established for a given y. And you see that you introduce this following map. This map is in general sensible on this. And then because of the contraction nature, you see that y can be written as f of x if and only if x is a fixed point of y. Now that's the whole idea that you use. Okay, so you show that from the properties of phi you compute phi derivative. Phi derivative can be computed, and I can show that phi derivative of x, norm of this is less than half. And therefore, once this is identified, now you see that you can easily show that the map is a contraction, and the contraction map assures the existence of an x for a given y. So this is the art. Okay. Then you see that you can also show that the map f from u to v, where v is equal to fu, is 1-to-1. So it's a 1-to-1 onto map, and you have got fa is equal to b. A belongs to u, b belongs to b. And therefore, once this is proved, then you see the map becomes an invertible map. F becomes an invertible map. So F inverse exists. F inverse is defined from V to U. Okay? And therefore, F inverse we denote by, so this is F, we denote the inverse map by G. So you have G of now it's a function of function rule. Okay, so what do you do? Okay, you write fx equal to y, then x is equal to f inverse of y. Okay, what is f inverse? This is equal to gy. Therefore, what do you get? You get g of y equal to okay. So you can talk about the derivative. How does the derivative work? You use function of function rule. G derivative at f of x operating over f derivative of x, this is equal to, you know that this is the identity map, x going to x, so this is the identity operator. Okay, so what do you get? So you write g derivative of y, and this is f derivative of x is what? X is equal to gy. Gy hello? Yeah, okay, okay, right. So g derivative of y, f derivative of gy, this is equal to I. So what does it mean? We want to calculate g derivative of y. So g derivative of y is equal to f derivative of gy yes. This is what you end up with. Okay. Now one of the results that you can prove is this, that if f is a C1 map on an open set E, that means it is defined everywhere on E and it's a C1 map, and f derivative is invertible everywhere on E. These are the two conditions. F is a C1 map, f derivative is invertible at every point on E, then you see that f maps every open set into an open set. So f is an open map. Now this is one of the results that you can prove. Okay, so let me just conclude with a very interesting example which I have taken one whole lecture to discuss in my channel. So I would suggest you to look into that for all details, but it's worthwhile to look at that example, and because it gives a lot of insight into two things. One, about the specific example. Secondly, this is also a general thing that I think since you are all teachers, you should know how to analyze various ideas and theorems, and you will have to put your hand on various examples, non-trivial examples, and analyze them, and that will give you insight into why certain results are valid and so on. So that's my suggestion, that you spend time on that. So that is also, I have done it while working on that example. I thought that I will spend one lecture specifically for that, to give you an idea how you go about analyzing examples. So it is instructive in a different perspective also. So let me just give this example. This example is very fascinating. I'm giving only the gist, but you can work on this. Look at this map. Suppose so this is a map from where uxy is defined as, and this is and vxy therefore your map is this: f of xy what does this map look like? So it's a map from R2 to R2. And you see that it is defined for every point here. Now let us simply apply the theorem and compute f derivative. F derivative of xy you can easily compute. This is represented in the standard basis by taking the partial derivatives. So you see du by dx, du by dy, and dv by dx, dv by dy. Okay. So du by dx is what? It is 2x, and dv by dx is going to be 2y. Then du by dy is 2y. So what do you get? When is it invertible? When it is invertible, this is invertible provided this matrix is invertible. Therefore, that gives you 4 not equal to 0, or x square is not equal to y square, or see it is along the lines x equal to y and x equal to these two lines. The function is not invertible. Everywhere else f derivative exists and is invertible. So except along these lines it is invertible. Now look at this map. What is the nature of this map? First of all, what is the range of this map? First of all, you see that the first component is x square plus y square. Therefore, it is certainly uxy greater than or equal to 0. Therefore, you see that the image, it will go into, it will take the value that it takes up will be always in this part. Okay. Now, what is the relation between u and v? Let us look at that. So, suppose this is the uv plane. Then you are mapping this over here. Okay. You take 2 copies of R2. It's not onto that. Still, you have to analyze. The second component is 2xy. Now, you can easily show that v is mod v is less than or equal to u. What is mod v? It is 2xy. and u is x square plus y square. So you see it comes from the following, namely that what is mod b? It is 2xy. The other one is x square plus y square. Now therefore their squares you take. So you see that you get x to the power 4 2x square y square is on this side. On this side it is going to be 4xy. Therefore if you push it to the one side, this is this, and you see that the square of this minus the square of this is greater than or equal to 0. This is always greater than or equal to 0. So from that you get this is less than or equal to this. Therefore you see that V is mod V is less than or equal to mod U. So you have a wedge shaped region coming. This is U equal to V. This is U equal to minus V. So the image is essentially confined to this region and not outside. So the whole space gets mapped to this wedge under this map, and that's the interesting aspects. And you see that these two lines, where do they go? This is when you put x equal to y, what happens? You get 2x square here, or x equal to minus y, you get 2x square here. So what about here? If x equal to y, you get 2x square here. So they are equal. So u equal to v. If you put x equal to minus y, that is this line, then its image is again the line u equal to minus v. So you have got this whole line going over to this, and the whole line going over to this line. These are the boundaries that you have. And what you can show is that this portion maps into this, this portion maps into this, this portion maps into this, and this portion maps into this. Okay, so corresponding to any UV that you take here, there are 4 different points in this space. 4 different points in this space. Oh, now why I make this statement? Suppose xy is here and it maps to UV, say. Then you see that you look at the diametrically opposite point. Minus xy also gets mapped to the same point, because you see that x square plus y square, 2xy with both the minus sign coming, it will become twice mod x mod y. Okay, so you get this result, the same result. Okay, so these 2 points get mapped to the identical point. And similarly, if you take the reflection on this, you can show that they go to the same point. And so it's a very nice map. These wedges actually go over to the single wedge. What your inverse function theorem says is the following: if you are not on these lines where you are in trouble, if you are at some interior point here, okay, and at some interior point here, okay, if you are at some interior point here in any of these regions, avoiding this, you have a neighborhood which does not contain these lines, then this is your U, and there is a corresponding V which doesn't touch the neighborhood. So from U to V there is a 1-to-1 onto map. Okay, so the map is invertible, and all these statements of the theorem holds. I am sorry to rush through this. Yeah, I think that's a nice time to stop. It is 1:15. Probably I have exceeded some 15 minutes, but then that is not possible to avoid. And I hope you enjoyed the lecture. But I would certainly suggest you to all those who are interested should really spend some time looking into my channel, and that the discussion on inverse function theorem, which will certainly give you much deeper insight into this. Not only that, I have taken pains to analyze the proof thoroughly with a lot of figures, pictures, and all sorts of things, as it is customary in my lectures. Thank you very much. Okay, so with that I conclude.